Hi, I'm Ned, and I make games. Have you ever wondered how shaders work in Unity? Or do you want to write your own shaders for the Universal Render pipeline, but don't really want to use the shader graph? Either because you need some special features or just prefer writing with code, this tutorial has you covered. Today we're diving deep into material options to give us some more tools to create realistic visuals. With physically based rendering, also called PBR, we'll implement normal mapping, metallic workflows, more transparency blending modes, parallax occlusion, and clear code effects. I'll end with a section outlining techniques to optimize texture use and make the shader your own. If you prefer written tutorials, check out the article version of this tutorial linked in the video description, as well as links to the rest of the tutorials in this series. If you're starting here, I do recommend downloading the starting scripts from the video description so you have something to start from. Before I move on, I want to thank all my patrons for helping make this series possible, and give a big shout out to my next-gen patrons, Michael Samuels and Casey Vaughn. Thank you all so much. Well, with that, let's get started. So far, we've used the blend-phong shading algorithm in MyLit. It's great for simple objects, but we can do better. Most rendering engines have settled on a standard shading paradigm called physically based rendering, commonly abbreviated as PBR. It simulates realistic lighting using a bidirectional reflectance distribution function. Thankfully, Unity has programmed this already for use in the default lit shader. It's easy to reuse our implementation in our own MyLit shader. In the forward lit pass fragment function, change the final function call to universal fragment PBR. It accepts the same arguments in Unity 2020 and 2021, so it's safe to remove the #if branch. PBR includes specular lighting by default. The #define in the shader file is not necessary anymore. In the scene view, things will look very similar. If you're on Unity 2020, lower the material's smoothness to a value between 0 and 1. In fact, we should enforce this in the inspector. In the .shader file, change the _smoothness property to a range type, with bounds between 0 and 1. The inspector renders a slider and clamps the value between the minimum and maximum. That's really all it takes to use PBR in your shaders, albeit a bare bones version. We'll implement more features shortly. Right now, notice the more realistic specular highlights. In this series, I won't go into the math behind the BRDF or PBR algorithms, but if that does sound interesting to you, please let me know in the comments. As a shader gets more and more sophisticated, the need for better debugging tools only grows. We used the frame debugger in the previous section. It's useful to view draw order, but what if you need to check the value of a variable? In C#, we would use debug.log, but HLSL has no similar function. Well, the fragment function outputs colors, and as we know, colors are really just numbers. We can use them to visualize any value as long as the value ranges between 0 and 1. For instance, it's useful to output a normal vector as a color. There are a couple small steps to make that happen. First, remap each component to range from 0 to 1. Since normal vectors are normalized, the length is always 1, and each component ranges from -1 to 1. So we can remap them by adding 1 and dividing by 2. Second, fragment outputs a float 4, while normal vectors are float 3. Fix this by appending a 1 to the normal vector using the float4 constructor. When viewing the results, you can interpret redder values as normals pointing in the positive x-axis, green in the y-axis, and blue in the z-axis. These colors handily match Unity's XYZ gizmo. Here, for example, are the colors corresponding to each cardinal direction. You can use this technique to visualize any value. We've done normals, and here's UVs. You can even output smoothness, or scaled world position, or really anything you'd like. This is a debug.log of shader development. It is a little crude, but it's a good place to start if you run into a problem. Unity 2021 has a new feature called the Rendering Debugger, which makes many common outputs automatically available. MyLit should support a bunch of these. The logic to support this feature is inside Universal Fragment PBR. Many views are just output data fed into the input data and surface data structs. To support a few more views, set the clip space position field in input data, and add a shader feature to the forward lit pass. There are still some views that MyLit doesn't support, in which case it will appear either black or white. As we progress through this tutorial series, these gaps will mostly be filled out. But unfortunately, if you're using Unity 2020, you'll need to stick with old-fashioned debugging methods. You've probably already used normal maps if you've ever worked with a 3D model. Also known as bump maps, these textures encode directions and modify the model's normal vectors. Remember that normal vectors determine the strength of diffuse lighting around the model. You can cheaply and easily add detail just by using normal maps. Before we implement normal mapping, let's understand how they work beneath the hood. Textures store colors, but these colors are just numbers. We can interpret them as normalized vectors, similarly to how we output debug normals a few minutes ago. Each pixel stores one vector, remapped to range between 0 and 1. To reverse this, multiply by 2 and subtract by 1. This gives us a vector centered around 0. If you plugged in a normal map and tried to output these vectors, it would not look correct. There are two reasons. Number 1, Unity encodes normal maps in a special format optimized for normal vector storage. This is why Unity frequently bugs you about flagging textures as normal maps in their import settings. URP has a function to decode normal map texture samples called unpackNormal. It also includes the remapping step. Outputting that looks slightly better, but there's still something wrong. The normals are all kind of bluish, pointing in the Z direction, and they don't change when the model rotates. If you took this vector stored in the normal map and then tried to use it to apply lighting, it's obvious that you're missing a step. Vectors in normal maps exist in a special frame of reference called tangent space. The easiest way to visualize it is to picture a globe. Up points towards the North Pole, while the right and forward vectors point perpendicular directions out of the equator. Now picture yourself standing on the globe's surface. From your perspective, up points above your head, right along your right arm, and forward in front of you. You now exist in tangent space. It's the perspective of an object standing on the surface of your mesh. In tangent space, the up, right, and forward vectors have special names. The up vector is pretty obviously the mesh's normal vector. The right and forward vectors are called the tangent and bitangent. Notice that these directions change relative to world space, depending on where you stand on the globe. That's all well and good, but in the world of shaders, the light, camera, and all other data used are in world space. The normal vector must be there as well if we want to use it in lighting. Thankfully, it's easy to convert a vector from tangent space to world space using something called a change of basis transform. A basis is the mathematical name for the coordinate axes, x, y, z in world space, or tangent, bitangent, normal in tangent space. If you have the basis directions of one space given in terms of another, it's easy to convert points between the two spaces. In this example, in 2D, we want to convert a point from tangent space to world space. Given the tangent and bitangent directions in world space, we can multiply each basis direction with the corresponding component in the point and add the products together. The point 2, 1 equals the tangent vector times 2 plus the bitangent vector times 1. So back to our shader, we need to get the tangent bitangent normal basis directions in world space. We already have the normal, given to us through the mesh data. With that, we could technically just pick any two vectors that are perpendicular for the tangent and bitangent. However, in shader development, we define the tangent and bitangent so they correspond to the model's UV coordinates. Revisualize the globe, but now overlay it with simple UV values, resembling the latitude and longitude. The U coordinate is red, while the V coordinate is green. The tangent vector points in the direction of growing U value. In other words, if you walk in the tangent direction, the U value under your feet will always increase. Similarly, the bitangent points in the direction of growing V value. This works out really well. Since normal maps are just a texture applied to the model with UVs, the tangent and bitangent align with that texture naturally. If you unwrap the globe and watch where the tangent and bitangent point as you walk around, from the perspective of the normal texture, they always point in the same direction. Meshes store the tangent and bitangent vectors in the mesh data, just like normals. We now have the entire tangent space basis in world space, and we can convert a vector extracted from the normal map to world space. This gives us correct values for lighting. Whew, so that was a lot of math, but I feel it's important to really understand how normal maps work. They're fundamental to shader development, and you'll be using them a lot. Let's get started programming. First, open mylit.shader and add another texture property. Flag it with 2 attributes. First, the no-scale offset attribute hides the tiling fields in the inspector. This is preferable because the normal map should match the color map. Second, this normal attribute prompts Unity to check that any texture placed inside is correctly encoded. White is not a good default value for normal maps. White, or 111, will generate weird unnormalized normals pointing diagonally. The default value should act as if no normal map is present, using the mesh vertices normal vectors for lighting. The bump default has a value of 1/2, 1/2, 1, which is a periwinkle-like color. It resolves to the 001 tangent space vector. In mylit.common.hlsl, add the texture declaration. In the forward lit pass, we need the mesh's tangent and bitangent vectors. Tangents are stored in a vertex data stream with a tangent semantic. Like normal, these tangent vectors are in object space. I did lie earlier though. Bitangents are not actually stored in the mesh, at least not directly. Instead, we can derive them from the normal vector, tangent vector, and a special bitangent sign value. Unity stores the sign value in the tangent semantics W coordinate. We also need the tangent and bitangent in the fragment stage, requiring a new tangent field in the interpolator struct. It will be in world space by now, and also still contain the bitangent sign. Tag it with the next available text chord semantic. In the vertex function, we need to convert the tangent space vector to world space. The getVertexNormalInputs function has an overload taking the tangent vector and bitangent sign, outputting the world space tangent vector. Store this in output, passing along the bitangent sign as a W component. Now the fragment function has everything that it needs. First, calculate the tangent space normal vector. As mentioned earlier, Unity encodes normal maps in a special way. Use this URP function to decode the tangent space normal vector inside. Next up, calculate the tangent space basis. We have the normal and tangent, but not the bitangent. Given any 2 different directions, there are exactly 2 directions perpendicular to both, a direction and its opposite. Use the bitangent sign to choose a single vector between them. URP will calculate this for us in the createTangentToWorld function. Pass it the normal vector, tangent vector, and bitangent sign. It returns a float 3x3 matrix, which is simply 3 float 3 vectors stacked together. You can think of a matrix as a 2-dimensional array or a list of vectors. Remember the formula to convert a vector from tangent space to world space? Turns out that it's pretty easy to implement this in HLSL using matrix multiplication. The function transformTangentToWorld multiplies the tangent space normal vector from the normal map with the tangent-to-world matrix that we just created, producing a world space vector. We can use this finally to calculate lighting. Normalize it to prevent rounding errors. Now, I think some testing is in order. Return this normal vector, remapping it appropriately. In the scene editor, find a test normal map and, in the texture importer, set it as a normal map. Apply it to your material and make sure everything makes sense. If you remove the normal map, the displaying color should not widely change. Rotating the model should result in rotated normal vectors. It should also work with double-sided rendering. Return to the code and remove that test line. Then set the normal vector in lighting data. Apply the normal map to your material again, and marvel at the added detail. Sometimes the lighting effect is a little too strong, and there's an easy way to adjust normal map strength without editing the texture. Add a float normal strength property to mylit.shader. Usually a range from 0 to 1 is recommended. Add the declaration in the common HLSL file. Then switch the unpack normal function with unpack normal scale, passing the new strength value. And that's all there is to it. There's one more wrinkle that you should know about. When choosing a normal map, URP and our shader assume the bitangent points in the direction of growing V, like I explained earlier. In other words, it should point from the bottom to the top of the normal map. Some other programs use the opposite bitangent. Make sure that your normal map follows the OpenGL convention and you'll be good to go. Finally, in Unity 2021, we can do a bit more to support some more views in the renderer debugger. Set the tangent to world transformation matrix in lighting data, and the tangent space normal in surface input. Note that even though it's unused in 2020, normal TS does exist in surface data in that version. Then, signal to the debugger that the shader supports normal maps by defining this keyword in the .shader file. The renderer debugger can now display tangent space normals, and also remove normal mapping from lighting. So that's the basics of normal mapping. There's a lot of complex math behind it, but URP does do a good job helping you get by without thinking about it too much. Be sure to leverage normal maps, because they're a cheap way to really help your models shine. One cool aspect of PBR shaders is their ability to create metallic surfaces. URP's Universal Fragment PBR function makes metals really easy to implement in our shaders. First, add a Metalness float property in mylit.shader, which ranges from 0 to 1. In mylit-common.hlsl, declare this new float property. Then, in mylit-forward-lit-pass.hlsl, sync the metallic field and surface data to this new property. In the scene editor, try it all out. Notice how metallic strength changes the way highlights affect the material. It will look quite dark right now, mostly because we haven't implemented reflections. We'll set this up in the next part of the series, so look forward to that. Objects are rarely completely metallic, and it would be helpful to vary metalness across the mesh. This is pretty easy to do with another texture. We can store metalness values in the texture and read them using UVs, like the color and normal map. Using the texture to turn on and off a shader feature is commonly called masking. In your shader file, add another texture property for the metalness mask, and a new property to the common HLSL file. In the fragment function, sample the metalness mask. Since metalness is a float, only save the red channel's value. Multiply that with the metalness strength property and set it in surface data. Back in Unity, set a metallic texture in your material. Since this texture encodes special data and not colors, it's a good idea to turn off sRGB setting in the texture importer. Be sure to turn this off for any texture that stores data, like masks or lookup textures. With that out of the way, only areas where the mask is white should appear metallic. You can verify this by looking at the metallic view mode in the rendering debugger, or just outputting metallic string. Compare this with your mask by placing the mask in the color map slot if you'd like. The lit shader actually has two distinct modes to handle metallic surfaces: the metallic workflow and the specular workflow. The specular workflow uses a specular color texture to determine the color of specular highlights over the model. The brightness of the specular color controls the metalness at that point. To enable the specular workflow, first, hash define this keyword in the forward-lit pass block of mylit.shader. We'll also need properties for the specular texture and tint. Define them in mylit-common.hlsl as well. In mylit-forward-lit-pass.hlsl's fragment function, sample the specular map and multiply the color by the specular tint. In specular workflow mode, Universal Fragment PBR actually ignores the metallic value. Use this hash if block to set the specular color if specular setup is enabled, and metallic otherwise. In the scene view, try adding a colorful specular texture to see how it affects everything. Notice that the specular highlight is kind of the inverse of the surface color. This is optics at work. You can also inspect specular color in the renderer debugger. You might have noticed that we use keywords to switch between metallic and specular workflows. It's easy to add a property to toggle keywords on and off, with no extra custom inspector code required. In my lit.shader, add a float property with a special toggle attribute. The keyword name to enable and disable goes inside the attribute. The property name doesn't really matter, just make it something relevant. Finally, set the property value to 0 to disable the keyword by default. In the forward lit pass block, replace the hash define with hash pragma shader feature. Since it's only used in the fragment stage, set it as a local feature only used in the fragment stage. In the scene editor, you can now easily switch between metallic and specular modes. While we're on the topic of specular lighting, it would be very nice to vary a model's smoothness across its surface. We can do that with another mask texture, this time containing smoothness values. Add a smoothness texture to the shader properties, declare it in the common file, and sample it in the forward lit pass fragment function. Using the red channel, once again, multiply it with a pre-existing smoothness property, and then set it in surface data. In the scene editor, try adding a smoothness mask. Turn off sRGB. That's pretty cool. These textures really go a long way. If you work with other 3D programs, you might see some of them use a gloss or glossiness map. This is just another name for a smoothness map. Some others use roughness mask, which is just the inverse of smoothness. In other words, roughness equals 1 minus smoothness. If you want to use roughness in your shader, just invert the texture sample before setting it in the surface data. You could even add a property to optionally do this for you. However, for the rest of this tutorial, I'm just going to support simple smoothness masks. One other thing to mention. I know that those of you with shader experience might be cringing at our use of separate textures for all of these masks. At the end of this video, I will explain how we can optimize this a bit. Put it in the back of your mind for now. My lit already has full transparency support, but URP's lit shader has a few extra transparency modes that we could add. Additive, multiply, and pre-multiplied. Additive and multiply modes are very useful for particles, while pre-multiplied mode helps simulate glass. The bulk of this work lies in the custom inspector. Add a new blend type enumeration with the 4 modes that we want to support: alpha, pre-multiplied, additive, and multiply. To store the currently selected blend mode, we'll use another property similarly to how we handled the surface type. Get and set this property in the onGUI function. The main difference between all these blend modes is the source and destination blend settings that they use. Remember, these instruct the renderer how to combine colors from the fragment function with colors already on the screen. In Update Surface Type, read the blend type property. In the switch statement where we set blend modes before, add another switch statement inside the transparent blend case. Within that, set the appropriate source and destination blend modes for each case. Let's take a look at each. The alpha mode looks like we're used to, blending based on the alpha value of the source pixel. In this mode, the rasterizer multiplies the source color by the alpha value, the destination color by 1 minus the alpha value, and then adds them together. Pre-multiplied mode assumes alpha has already been multiplied with the color and stored in a texture's RGB values. That kind of explains the name, huh? Alpha has been previously multiplied. In this case, the source blend type should be 1, so alpha isn't applied again, but the destination should still behave like normal. This gives artists better control over how a transparent object looks. Effectively, brighter pixels are more opaque. Additive mode is mathematically the inverse of pre-multiplied mode. In this mode, the source is affected by alpha, but the destination is not. The destination color is only ever added to. Additive mode lightens the scene, and it's great for particle effects like lightning and fire. Finally, multiply mode is for specialized use. It utilizes a new blend mode called source color, which is simply the source pixel's RGB values. Multiply mode completely ignores alpha, just multiplying the source and destination together. It tends to darken the scene, sometimes useful for otherworldly effects and masking. In mylit.shader, don't forget to add the new blend type property. Check the new modes out in the scene. It's pretty cool how we can get so many effects just by manipulating blending mode. URP further enhances the pre-multiplied mode by having lighting affect the material's alpha. It's again wonderful for glass, where specular highlights appear opaque. Universal Fragment PBR handles everything, and we only need to enable a keyword, alpha pre-multiply on. Back in the custom inspector, enable or disable this keyword appropriately. Then in mylit.shader, add a shader feature to the forward lit pass. In the scene editor, try it out. Specular highlights definitely appear more opaque. Some objects, like electronics or magical artifacts, have small glowing parts. It's really too expensive to use real lights for these fine details, but we can do our best with something called an emission texture. It defines glowing areas on the mesh. Emission is pretty easy to implement. Add an emission texture property in mylit.shader, as well as an emission tint. The HDR attribute flags this tint as a high dynamic range color, meaning that its components can take values greater than 1. This is useful in combination with some post-processing effects like bloom, which we'll talk about more later in the tutorial series. Add the new properties to the common HLSL file, then sample the emission texture in the forward lit pass fragment function, multiply it with the emission tint, and store it in the surface data. That's honestly all you need to do to support emission. Test it out by grabbing an emission texture and adjusting the emission tint. Note that if the emission tint is black, no emission will appear. You can check out emission in the renderer debugger too. If you want to disable it temporarily, there's an option to do that in the lighting features enumeration. Emission works by ignoring shadows and overexposing affected areas. It doesn't actually light the scene, unfortunately. We can sort of fix this by tying it into baked lighting, which will happen in part 5 of this series. URP's complex lit shader has a few cool options that we should look at, the first being parallax occlusion. Parallax is a method of simulating depth by scrolling textures based on their distance from the camera. In parallax occlusion, we move UVs around to simulate small divots in the material. Let's see how it works. First, we need another texture called a height or displacement map to determine which areas are depressed below the surface. Next, pretend this height map actually deforms the mesh. When evaluating the parallax for a specific UV coordinate, cast a ray from the camera through the UV until it hits the imaginary deformed surface. Project the impact point back onto the texture and use that new UV coordinate to sample the color map, normal map, etc. In this way, UVs change based on the view direction, more for areas depressed by the height map. The effect gives the illusion of depth. Luckily, all the math behind the ray casting and such is handled by URP functions. To get started, add a height map and a parallax strength property to mylit.shader. In mylit-common.hLSL, add declarations for these new properties. In mylit-forward-lit-pass.hLSL, rearrange code a little bit so the normal and view direction are calculated before any texture sampling. We need to calculate a new UV based on these values. In the process, use these position and view direction variables throughout the function instead of the values in input. The parallax occlusion mapping algorithm needs view direction in tangent space, since the imaginary surface formed by the height map exists in tangent space. URP provides a get view direction tangent space function to do just that. Include SRP's parallax mapping.hLSL file to make it available, and pass it the world space tangent, with the bitangent sign, normal, and view direction vectors. Get view direction tangent space needs the vertex normal in an unnormalized state. This is an important bit of info to keep in mind. Now call the magic function parallax mapping to do the work. It requires the height map and sampler. To pass textures and samplers to functions, you must use this special macro. It exists to get around platform differences, similarly to texture declarations. Then pass the parallax mapping the tangent space view direction, parallax strength property, and the current UV. Parallax mapping returns the amount to offset UVs, according to the parallax algorithm explained above. Add the offset to the current UV, and be sure to use this new UV to sample all the other textures. Check it out in the scene. Find a height map and set the parallax strength. It doesn't take much to create a really strong effect. Usually a parallax strength of around 0.05 is plenty. This is as far as complex LITS parallax mapping goes, but there's a lot more that we could do with it. Would you be interested in learning more in another tutorial series? Please let me know in the comments. Besides parallax, there's another advanced feature hidden away in the complex lit shader, clear coat. You know that shiny coating on car paint? Clear coat can recreate that effect. Like Emission before, it's easy to implement. Add a clear coat strength mask and a float property. Clear coat emulates a transparent coat of paint on top of a surface. It can have its own independent smoothness value. Add a clear coat smoothness mask and a strength property as well. In the for lit pass block, define the _clear coat map keyword, so universal fragment PBR includes the clear coat calculation. In mylit common, define new textures and float properties. In mylit forward lit pass.hlsl, sample the masks, taking their red channels and multiplying with the float strength properties. Set the clear coat mask and clear coat smoothness fields in surface input. That's basically it. Clear coat is useful for many different objects, like cars, furniture, or even candy. It is pretty expensive though, basically requiring 2 BRDF calculations per material. Consider leaving clear coat out if you don't need it. With clear coat under our belt, we support just about all surface options built into URP. However, our shader has ballooned quite a bit, and now is a good time to think about slimming it down. In future parts of this tutorial series, I'm going to stick with this general purpose unoptimized shader. However, once you know exactly which features your personal shader requires, I would revisit the techniques in this section to speed it up and also make it easier to use. Step 1. Figure out which features you need. Do you always use metallic workflow? Remove support for the specular workflow, including the specular color texture and tint. Removing expensive features like clear coat, parallax, or normal mapping is usually worth it. It's also possible to toggle a feature on or off using a keyword. For example, say only some of our materials need normal mapping. We can set up an inspector to disable a keyword when no normal map texture is assigned to the material. In mylit custom inspector's update surface type function, use get texture on the material. Enable or disable the normal map keyword based on if it returns null. In order to call update surface type when the normal map changes, move the base.onGUI call to between the begin and end change check functions. In mylit.shader, change the hash define to hash pragma shader feature. In mylit forward lit pass.hlsl, use the mesh's normal vector if normal map is not defined. This corresponds to a tangent space normal vector of float3,001. If you go a step further and also remove parallax mapping, you have no real need of tangents in general. It's important for performance to keep the interpolator struct as small as possible, since each variable is more that the rasterizer has to interpolate. Using a keyword there works great. Another useful technique is called channel packing. Notice how the various mask textures only use a texture's red channel. What if we combine several masks into one texture? For instance, we can put the metallic mask into red, smoothness into green, clear coat strength into blue, and clear cut smoothness into alpha. Texture sampling is a big resource hog, especially on mobile platforms, and it's very nice to merge 4 samples into one. You can construct this texture using Photoshop or any other photo editing software. Treat each mask as a grayscale image and place them each into one of the color channels. Many times, alpha channels aren't used, they're prime real estate for masks. If your material is always opaque, you can hide a mask in the color map's alpha channel. The specular color and emission textures alpha channels are usually unused as well. Heads up! we will be adding one more mask texture later on in this series, an occlusion mask. This controls the strength of ambient lighting across the model. If you go ahead and optimize your shader now, leave room for this one texture as it's quite important. Adding cool surface features is one of my favorite aspects of shader development. Now we can make metal objects, glass objects, bumpy objects, and a brand new car. We've done a lot with our own material, but it's time to look outward. In the next tutorial, I'll focus on a hotly anticipated topic, advanced lighting. We'll look at how to support multiple point and cone lights, baked lights, occlusion textures, reflection probes, light cookies, and more. For reference, here are the final versions of the shader files after completing this tutorial. This doesn't include any optimizations mentioned in the last part of this video. You can also view all of these on GitHub from a link in the video description. Please stay tuned, subscribe, and press the bell to be notified when my next tutorial video goes live. If you enjoyed this, consider liking the video as well. It really helps out with the YouTube algorithm. Are you having any issues or questions? Feel free to leave a comment or contact me on social media. I read all comments and I'll reply when I can. I want to take another moment to thank all my patrons for helping make this video possible, and give a big shout out to my next-gen patrons, Michael Samuels and Casey Vaughn. Thank you all for your support, it really does mean a lot to me. If you'd like to download all the example shaders from this tutorials and all my others in an easy-to-use zip file or Unity project, consider joining my Patreon. Thanks so much for watching. Make games.